And welcome back as we continue our celestial journey through our own solar system. We, of course, had previously looked at asteroids and their role in our solar system, but let's go ahead and shift gears to look at that of comets, which, instead of being more rocky in nature, are much more icy. So we start discussing comets. The first thing we have to understand is how they differ from asteroids is primarily in their icy composition. And this difference is what causes them to brighten dramatically as they approach the sun, forming a temporary atmosphere. In some early cultures, these so-called hairy stars were considered omens of disaster. Now today we no longer fear comets, but eagerly anticipate those that come close enough to us to put on a good sky show. So when we start talking about the appearance of comets, we already heard that they're kind of hairy in some of their appearance. But a comet is really just a small chunk of icy material, typically a few kilometers across, that develops an atmosphere as it approaches the sun. Now later, there may be a very faint, nebulous tail, extending several million kilometers away from the main body of the comet. Now comets have been observed from the earliest times. Accounts of comets are found in the histories of virtually all ancient civilizations. Like we said, they often would mistake them and pretend as omens of doom. The typical comet, however, is not spectacular in our skies, instead having the appearance of a rather faint diffused spot of light, somewhat smaller than the moon and many times less brilliant. Now, one thing to keep in mind though is that a comet and a meteor are not the same thing. It's easy to kind of get them confused because they're both lighting up in the night sky, but there is a difference. Like the moon and planets, comets appear to wander among the stars, slowly shifting their positions in the sky from night to night. Unlike the planets, however, most comets appear at unpredictable times, which perhaps explains why they frequently inspired fear and superstition in earlier times. Now, comets typically remain visible for periods that vary from a couple of weeks to several months. Note that the still images of comets, like so if you just took a picture of it, give the impression they are moving rapidly across the sky, kind of like a bright meteor or a shooting star. But when you look at such images, it's very easy to confuse up a comet and a meteor because, again, they have kind of a similar appearance. But when you take a look at a comet in the night sky versus a meteor, well, the meteor is going to burn up in our atmosphere and be gone in a few seconds. It's just a quick streak of light and it's gone. Whereas a comet may be visible for weeks in near the same part of the sky. So let's go ahead and look at the comet orbits. The study of comets as members of our solar system dates from the time of Isaac Newton, who first suggested that they orbited the sun on extremely elongated ellipses. Newton's colleague Edmund Halley developed these ideas, and in 1705 he published calculations of all 24 comet orbits. He noted that the orbits of the comets had appeared in the years 1531, 1607, and 1682, and these were so similar that all three could well be the same comet returned to perihelion at average intervals of around 76 years. We now know that Comet Halley has been observed and recorded since 239 BCE at intervals ranging from 74 to 79 years. Now, the period of its return varies because you notice it's not an exact number here, and this is because of orbital changes produced by the pull of the giant planets. So as it passes through the giants, those giants are causing a slight variance on its orbit, and that's why we have this range of 74 to 79 years. And so that actually gets us into our next piece to know about comets, is that of a short period versus a long period comet. Only a few comets return in a time shorter than a century or two, like Comet Halley does. These are called short period comets. Many short period comets have had their orbits changed by coming too close to one of the giant planets. Now, most comets that we know of actually have long periods, and will take thousands of years to return, if they return at all. Now, we were visited by two bright comets in recent decades. First, in March of 1996, came Comet Hyakutake with a very long tail. A year later, Comet Hale-Bopp appeared and was bright as the brightest stars and remained visible for several weeks, even in urban areas. Now, when we start talking about comets and their composition, the first thing to understand is the comet's nucleus. When we look at an active comet, we see it is a temporary atmosphere of gas and dust illuminated by sunlight, which we refer to as the comet's head or the coma. Now, since the gravity of such small bodies is very weak, remember most of them are nothing more than maybe a few kilometers, the atmosphere is rapidly escaping all the time. And it has to be replenished by new material, which has to come from somewhere within the body. Now, the source is the small solid nucleus inside, again, just a few kilometers across, usually hidden by the glow from the much larger atmosphere surrounding it. The nucleus is the real comet, so the actual chunk that's flying through space, the fragment of icy material responsible for the atmosphere and for the tail. So, let's actually look at the comet's approach. Now, the spectacular activity that allows us to see comets is caused by the evaporation of cometary ices heated by sunlight. Beyond the asteroid belt, where comets spend most of their time, these ices are solidly frozen, like there's no movement. But as the comet approaches the sun, it begins to warm up. If water is the dominant ice, significant quantities vaporize as sunlight heats the surface above 200 Kelvin. Typically, this happens beyond the orbit of Mars. The evaporating water in turn releases the dust that was mixed with ice. Since the comet's nucleus is so small, its gravity cannot hold back either the gas or the dust, both of which then flow away into space at speeds of about 1 kilometer per second. Now, the comet continues to absorb energy as it approaches the sun, so it's getting closer and closer, so it's getting more and more energy. A great deal of this energy goes into the evaporation of its ice, as well as the heating of the surface. However, recent observations of many comets indicate that the evaporation is not necessarily uniform, and that most of the gases released in sun spurts, perhaps confined to a few areas along the surface. Expanding into space at a speed of about 1 kilometer per second, the comet's atmosphere can actually reach an enormous size. The diameter of a comet's head is often as large as Jupiter, and it can sometimes approach a diameter of 1,000,000 kilometers. So it can be much larger than what we would expect the size of the actual nucleus to be. Now, when we start talking about the comet's tail itself, most comets develop tails as they approach the sun. The comet's tail is simply just an extension of its atmosphere, consisting of the same gas and dust that make up the head. Now, the orientation of a typical comet tail changes as the comet passes perihelion. Approaching the sun, the tail is behind the incoming comet head, as we can see here in this image, but on the way out, the tail actually will precede the head. The two different components that make up the tail, the dust and gas, actually act somewhat differently. The brightest part of the tail is what we refer to as the dust tail, to differentiate it from a fainter, straighter tail made of ionized gas, which we refer to as the ion tail. Now, the ion tail is carried outward by the streams of ions emitted by the sun. The smoother dust tail curves a bit, whereas the straight ion tail is pushed more directly outward from the sun by our star's wind of charged particles. Now, if we actually want to truly observe a comet, what do we need? Well, the first thing we did is we took some spacecraft and threw them up in space, just like how we observed many other things, and the Rosetta mission actually gave us an up-close view of Comet 67P's surface. Now, the spacecraft verified that the comet's dark surface was covered with organic carbon-rich compounds mixed with sulfides and iron-nickel grains. Now, the evaporation of comet ices was sporadic here on this comet and limited to small jets, and showed that comets like 67P could not have contributed to the deposition of water on our planet. So that means something else might have originally brought some of the source of water, or maybe comets of a different type. But comets that were like 67P couldn't have been responsible because the water that was here on this comet was a different type of water than what we find on our own planet.